All right, we are streaming, so we can get started now. Um, so how was that lab? I mean, did you guys finish the lab on Monday? So was that okay? All right. So what we'll do today is kind of continue on where we left off on Monday. I'm not really sure we can do the next lab just yet. Maybe, maybe not. Okay, so we'll take a look. Um, Kind of take a look at where we are now and kind of talk about how to translate from C control structure to assembly language. Okay. All right. So let's go ahead and take a quick inventory of things that we have learned up to this point, especially when it comes to the mnemonics or the instructions that we have been exposed to. The first few instructions we got introduced to is LDI, LD, and ST. These three instructions serve different purposes, although LDI and LD seem to do about the same thing, but they're different. LDI is going to load a constant into a register. So if you say, I want to initialize register C to 14, okay, LDI can do that. LD, on the other hand, is going to go to a memory location based on what a register is pointing to, grab the content at that location, and then copy that content to a register. So it also overwrites a register, but the source where it is getting the byte to overwrite the register has to come from memory, and where in memory is dictated by a register as well. It can be the same register. It's no problem. Okay, you can have an LDA and then comma and then in parentheses A. That works too. The ST instruction is the opposite of LD. It stores the content or it stores the value of a register to the content in memory pointed to by a register. So it's exactly the opposite of LD. So these three instructions were first introduced, and then we talked about the compare instructions. So if I just kind of follow these, so we talk about conditional branching, and a whole bunch of some other instructions. So we also talked about the halt instruction, which is kind of just the last instruction you want your entire program to have, so that it has one place to stop. Okay. We talked about the JMPI, the J quote unquote XI instructions. X stands for a flag, okay, and there are 5 flags in this processor. There's the carry flag, the 0 flag, the sign flag, the overflow flag, and the L or the less than flag, okay? So there are 5 flags, so we have 5 variants of the JXI instruction. So with JMPI instruction, it is unconditional, which means when you execute a JMPI instruction, whatever you specify as the operand, okay, is where you will go to continue execution. If you say JMPI 2020, okay, then you are going to continue execution at location 20 in memory. That's basically what JMPI does. JXI is like JMPI, but with a condition. So you can look at JXI as JMPI if and only if the flag mentioned is a 1. So that's the main difference between a JMPI and a JXI instruction. Now, exactly how is this done at the lowest level? In other words, how is this done using the multiplexers, demultiplexers, and stuff like that? The processor is the quote-unquote self-documenting medium, so you can actually refer to the architecture itself in Logisim and watch it happen and as you execute those instructions. So I strongly recommend that you guys study like that. Oh, I forgot to do one thing, because I've just made this slide for the other class, but I forgot to link it to this class too. So let me link it first. Let me grab that module first. This is a quick way to look at all the modules that I have written in time. You can see I'm down to 320 now. How many are applicable to this class? Well, not too many, okay? But you can go through the whole list if you're interested. And the URL to a list of all the modules is up here. You don't have to copy it now. When you replay the video, you can copy it at that time. So I'm just going to copy the link here, copy link address, go back to this class, and then add an external link here. So we're just going to add an external URL, paste, and this is how to study TTP. Add item, and now it should be added. So when you get to the end of here, once it's published, you should see it now. Okay, so I want to spend just a little bit of time because I think every single semester, every year, I get implicit questions. Okay, most people do not ask the question, but I can tell that they have that question. So the question is, how do you study text toy processor? In other words, how do I get ready for exam 2? Because exam 2 is certainly going to cover most of the material that we have been talking about. So it's a very short module, it's not long. So the first thing you need to do is to understand the major pieces of text toy processor. The first piece, okay, is the body, quote unquote body, of the simulated processor. So if I were to refer to it, it's just basically this entire thing, including the embedded architecture of the register bank as well as the ALU. The reason why I put those into a subcomponent is if I don't do that, I don't have enough room to design the entire processor. Okay, so especially the ALU, it is one pretty big component all by itself, although the interface of the ALU to the outside world is relatively simple and clean. Okay, so this whole thing, okay, now of course you're looking at a zoom in version of the processor. So if you zoom out a little bit, this entire thing, excluding the content of RAM and ROM, is what I call, quote unquote, the body of TTP, text toy processor. Okay, how do you study this? Well, there are a few things. First of all, you have to understand all the components first. What components are we talking about? Do you know what a multiplexer is? Do you know what a register is? Do you know what a demultiplexer is? We have very few demultiplexers, but they're there. Do you know what a RAM component is? Do you know what a ROM component is? If you zoom into the ALU, then you have some additional questions to ask yourselves. Okay, do you know, well, we have the same thing, demultiplexers and multiplexers. Do you know what an adder is? Okay, what are the inputs to an adder? What are the outputs of an adder? This is a subtractor. This is a bit shifter. Now, a bit shifter is pretty simple. Okay, all it does is to bit shift, but the operand order is important. There's bitwise NOT, bitwise AND, bitwise OR. Do you know what this subcircuit is doing? There's a whole bunch of AND gates and OR gates. Okay, they're here to calculate the overflow flag itself. This is a NOR. It is used to calculate the zero flag. And do you know how to use exclusive OR? Do you know what is a merger slash splitter and how to use it? Okay, so zooming back out, there's not really a whole lot more. I mean, I think I have just listed most of the components. There's one more. There's a decoder. That's it. So we got decoder, demultiplexer, multiplexer, register, splitter, wires, tunnels, okay, RAM, ROM, and registers. Okay, so those are the main components. So the first thing you need to do is to make sure that you understand each and every single one of those components really well. Okay, you can read the documentation. You can pull one of those components out and experiment with it until you feel that you're comfortable, that you understand what it does. Okay, so that's the first step. The second step is to basically just look at how they are all connected. Okay, LogicSim doesn't allow color coding, so what you can do is you can print it out on a piece of paper and then start to color code it. I would definitely use a different color and highlight the registers. The registers are very important because registers can store information. RAM can store information, ROM can do that too, but registers are very crucial to the operation of a processor. So they are major key components in a processor. So I would highlight those, okay? Then what about the multiplexers and demultiplexers and stuff like that? Well, they are basically just switches for train tracks. In other words, they are only necessary to understand when you say, I need to connect this to here. Okay? Then you have to look at all the multiplexers and demultiplexers in between and ask, how do I configure all of those switches in between to establish the path that I want to establish? So that's why they are somewhat secondary, in terms of understanding the whole architecture. The main registers, okay, there are 4 registers inside the register bank, but those are called general purpose registers. There are other key registers as well. This is the program counter. There's the instruction register. Here's the flag register, or flags register. Here is the microcode pointer, which is also a register. So these are the key important registers because they all control the execution of instructions. Now the 4 registers, A, B, C, and D, they're important, but they are only important once you know what instruction you're executing. Then you need to know, okay, are we overriding this register or the other register, or which register is providing the content to override locations in RAM. So that's the first part. Okay, so the first part is to understand the individual components and then understand how they're connected. The second main component is the microcode in ROM. There's only one ROM component here, and that is providing all the microcode slices. So one slice is basically a configuration of all the multiplexers, demultiplexers, registers, decoders, and so on and so forth at any given time, at a particular instant of time. So the slicing concept is really important because a lot of instructions, well, most instructions can be done with one single slice of microcode, but to get to that part, there are 3 cycles. Okay, they're all specified in the ROM. There's the fetch cycle, there's the decode cycle, and then there's the execute cycle. So you have to kind of understand which slice specifies the fetch cycle, which slice specifies the decode cycle, which also increments the program counter, and which slice, and then you have to look into the individual slices on a per opcode basis. Okay, so this basically forms the quote-unquote instinct of the processor. Okay, these are things that the processor quote-unquote natively knows how to do. Okay. All right, so continuing with this. So now you have the RAM component. The RAM component contains both the data to process as well as opcodes that you can specify, as a part of your program. So the concept of the relationship between an opcode and microcode is the microcodes implement the opcodes. The opcode gets decoded into the microcode pointer, but the microcode pointer can address up to 16 slices per opcode. So I can specify a fairly complex opcode and have it implemented by up to 16 microcode slices. Now, most of the instructions that we have are really simple. They can all be done with basically one single microcode. So are we okay so far with the main components? Okay, all right. So these are all the things inside LogicSim. So when you load up the processor, these are the components that are already here, including the content of ROM. The content of RAM is not included on this list because every time you hit Control-R or every time you reload the processor, RAM is all zeroed out already. Okay, so the content of RAM has to be loaded kind of more frequently because it doesn't come with the processor itself. All right, moving on. So the next component is called the assembler. Because without the assembler, we can already write programs and we can already run programs. But it's a very, 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 very tedious process. Because in order to write some code, let's say to find the absolute value of a particular register, you will have to kind of know the binary code of all the opcodes because you have to figure out, okay, which part of the opcode is constant, 1001. Okay. Which 2 bits specifies the first register? Where's the XX? Okay, we need register A, so XX is 00. Which is the other register? Let's say register C. It is 10. So now you have 1001 0010 as the opcode, okay, which is 772, okay? So 72 is the hexadecimal opcode. And, well, guess what? I mean, if you want to do it that way, you can certainly write a program like that, okay? So you right-click on here, you say Edit Content, you go to whatever location that opcode is supposed to go, and you say 72. There you go. Here's one opcode. Now you move on to the second one and the third one and so on. But when you get to the jump instructions, it gets even nastier. Because if you have to answer the question of where am I supposed to jump to, now you have to start counting these bytes, right? You have to start counting, go like, okay, 0, 1, 2, 3, 4, 5, 6, 7. Okay, I need to go to location 7. So now you specify 0, 7 after the JMPI opcode. If you count anything wrong, the program is not going to work, okay? If you need to insert instructions between already established instructions, you have to change all the addresses because it pushed everything after that, off by bytes. Okay, so it's a very, very tedious process if you are to do programming in machine code using your own way of figuring out the opcodes. Okay, you can do it a few times just to experiment, just so that you know how to do it. But in general, it is a very painful and tedious process. So that's why we have the assembler. The assembler, I'm just going to show you the assembler. You already know what the assembler looks like, but I'm going to show you anyway. So let's go to the shared folder. Go to processor and assembler. Okay, there we go. So the assembler is a tool to greatly reduce how much torque you have to go through to write a program in instructions. So in the source tab, you can now specify what we call mnemonics. So LDI is a mnemonic, CMP is a mnemonic, byte is a mnemonic, NOP is a mnemonic, and so on. So they're basically symbolic names of either opcodes or a family of opcodes. In the case of CMP, it is a family of opcodes because which two register are you comparing? Well, I mean, you can compare register A to B, B to A to C, C to A, and so on, right? So CMP as a mnemonic is actually the symbolic name of an entire family of opcodes. There's a whole bunch of opcodes corresponding to that name CMP. But it's okay because as far as you're concerned, you just have to say CMP and then specify the two registers that you want to compare. You don't even need to remember, oh, register A is 00, register D is 11, because that is automatically translated for you. So now you can focus on more of the logic of your program as opposed to all the details that otherwise you have to keep track of. The use of labels like L1, okay, L1 in this case is the address of whatever instruction or byte is right next to it. So L1 is the symbolic name of the address of the no op instruction on line 16. Well, without labeling, you will have to do the counting, okay, which is very tedious. Is it doable? Yes, it is doable, but it's not practical to do that, okay? So this is what the assembler does, okay? You give it mnemonics, you give it label definitions, you can even have comments, okay, to help it easier, to make it easier for you to understand the code. These intermediate, tabs here is, for debugging purposes. This is a list of all the mnemonics. It's not really intended for you to read, okay? This is a data-driven type of thing, so I use this to make the assembler work, okay? But you can probably see some of this stuff. If you look into the design of the assembler itself, you will probably figure out what these things are useful for. But this is a tab that you don't really have to pay attention to. This is a really useful tab because it shows you all the different phases and components of how a particular line is compiled or assembled to the bytes that represents it. Okay. And then we have output, which is just the location versus the content at the locations. And then this is the most important one because if you do assemble correctly, it doesn't complain about errors. This particular sheet inside the spreadsheet is giving you the code that you can download and upload or load into the RAM component directly. So if nothing bad happens, if there's no syntax error or any other types of error, then you go to this tab, you go to File, and then you say download as, and then you select CSV or TSV, and whatever file you save it to can now be uploaded to Logisim. Okay, I know it is not a one-click operation like code blocks. Okay, it is not simple like make enter. Then you get the executable. But it's much better than having you to have to hand assemble the code manually. Okay, so it still beats that. Okay, so this is the assembler. It is a tool to help you write your programs more effectively. So I'm getting back to the module here. Okay. So how do you study? Where do you start? Okay. So my suggestion, as I mentioned already, is to start with quote-unquote the body of the processor. Understand the components, understand how they connect. Okay. That's the first thing. You have to get familiarized with that map. Okay. Because even though the exam is going to be open book and open notes, okay, but if you're not familiar with the map, the next time if a question involves, okay, find the program counter and show me how it can potentially be connected to blah blah blah, okay, you don't want to waste your time to go through the sheet and go like, okay, but where's the program counter? So studying means getting familiarized with the map. Okay, I promise. Okay, in the exam, I'm not going to give you an entirely different map of the same design, just to mess with you and go like, where's the program counter? In the original sheet, it's over here, but then in the exam, I just move it somewhere else to make it difficult for you to find it. I'm not going to do that. Okay, that's not the point of the exam. So that means if you study the map now, it's going to be the same map in exam 1 or exam 2 and also the final exam. All right. So get familiarized with the positions of all of those things. If you are not really sure about how a particular component works, look up the library reference, design some experiments on your own, to check it out and figure out, okay, what does this do? Okay, use input pins and output pins, okay, to observe the output of a particular component by exercising the input. Okay, look up the definitions. Most of the components in this processor are not unique to this class. If you look up multiplexer, using Google, you will find a lot of references to explain, what a multiplexer is. Same thing for a demultiplexer and so on. So those concepts are not unique to this class. Now, the instructions are a little bit different because this is a processor that is only used in this class. So that means the instructions are also unique only to this class. So with this, you can't really use the internet to help you much, okay? So with this, what do? Well, everything is open sourced, okay? So I have one more section that talks about the open source concept, but what you need to do is to study the instructions. What do I mean by studying the instructions? Okay, so I will show you exactly what I mean by that. So let's say I want to figure out how JCI gets the job done, okay? I want to quote-unquote study JCI. The first thing I would do is to go to the opcode table. Okay, so the first thing I would do is to go to the opcode table, which is right here, and then I look up JCI, jump if the carry is set. So the JCI instruction is here, and we'll zoom in a little bit just so that it's easier to read. Okay, there we go. Okay, so here's the JCI instruction. I would read the opcode. Well, the opcode doesn't really tell you much, right? The opcode is just constant here. It doesn't have XX, doesn't have YY, because it doesn't rely on any registers. So there's no register component to the opcode. So the opcode is really quite simple. It's 4-4. Okay, 0100 is a 4, 0100 is the other 4. So 4-4 specifies this opcode. Okay, no big deal. This is the mnemonic. JCI is the symbolic name of that opcode, and it has one immediate operand. The immediate operand means it is just a constant. If you want to specify a number, you can do that. 16 is fine, okay? 25 is fine. But you have to make sure that location 25 is really where you want to go when the carry flag is 1, okay? So most often, the I is not an actual number, it's a symbol, because you use label definition to help you locate, oh, we want to continue execution here if the carry flag is 1. Okay, so I is usually a label, but in very rare cases, if you so decide that I want to use an actual number, it's perfectly okay too, syntax-wise. Okay, but the most important part is, what does it actually do? Well, this describes what it actually does in pseudo-C format. Okay, so what it says is the program counter is changed. How is it changed? What is the right-hand side of the assignment? The right-hand side of the assignment is a ternary operator or ternary expression. So now if you're not familiar or if you don't remember what a ternary expression is, look it up. Okay, it's a very standard C expression. It is also well supported by most languages that are based on C. So that means C++, Java, JavaScript, PHP, and so on. Okay, it's documented all over the place. C is the condition. If C is true, which means C is 1, then you just go to whatever the program counter is pointing to in RAM and return that, and that is going to be what you use to update the program counter. Okay, it doesn't seem to make sense, but it does, because the program counter is actually not pointing to the JCI opcode anymore, because the decode cycle increments the program counter. So by the time the microcode of JCI executes, the program counter is pointing to the byte next to the opcode of JCI, which is where you specify the actual destination, where you want to go. Okay, so that's the trick. What if the carry flag is a 0? Well, if the carry flag is a 0, according to this, we just add 1 to the current program counter and use that to update the program counter. Then you go like, why are we just adding 1 to it? Well, because the program counter at this point is pointing to the byte that specifies the address where you want to go. If the carry flag is cleared, you don't want to perform the jump. But you don't want to just leave the program counter as is, because otherwise it will use the byte that specifies the address as if it is the next opcode, which is not going to work. Okay? So that's why it has to skip the byte that specifies the address, so that the program counter in the fetch cycle will grab the actual next opcode instead of the address of this particular opcode. Is that okay? Okay, so now that we understand this part, what else can we do to study the JCI instruction? This is where most people would go like, but I don't want to do that. This sounds really, really cumbersome and difficult. The more reason why we should do it. Most things that are easy are not worth doing. So we right-click on the ROM, and we go to location 440. Why location 440? Because when the instruction or the opcode 44 is decoded, it would go to location 440 in ROM. Okay? Now, if you have a question of, but I don't understand why that is the case. Why is the opcode 44 going to decode to this address 440? Then it's time to restudy the body of the processor, because it's completely open. Okay, by understanding and studying the architecture itself, it actually would explain why 440 is important for 440 opcode, which turns out to be JCI in this case. Okay, so now you look at this number and go like, oh man, what are we looking at here? Well, we are looking at a bit pattern. So now you need to go take a look at the bit pattern and decode it. Okay, so you have to basically do the decode manually. You might think, but doesn't the processor decode it also? Can't I just use the processor to do this part? It's not the same, because if you do it manually, you would what you understand is going to stay in your head at least for the rest of this semester. If you just rely on the processor or logic sim to do it, the moment it's done, you won't remember a single thing. Okay? So now we look at this number. We look at 440. Okay, I'm just going to copy the number here. It is 1880006. So you now decode it. Okay, it's 0001. That's the 1. 1000. That's the 8. 1000, which is the other 8. 0000 for the first 0. Second, third, 0110 is the 6. Okay, so now we got a whole bunch of bits. Okay, the right hand side is bit 0, and then 1, 2, 3, all the way up to bit 20 and bit 21. No, I take it back. We go all the way to bit 24 and bit 25. Okay, so there are 26 bits to the output of the ROM. So you look at all of these bits and you ask, what is that going to do? Now here comes the really tedious part, especially when it's your first time doing it. It's going to be a little bit painful. So look at the design here and go like, okay, most of the zeros are not really of major concern to us unless it's controlling a multiplexer or demultiplexer, but the enabling and the enabling of registers is what we're looking for. Okay, so we want to look at these ones and go like, okay, where is this one going to? It's bit 1. So now you go back to the design, and it's time to zoom back in because otherwise we can't really find those things. So you look at this. Okay, bit 1 is here. So bit 1 connects to the tunnel called RAM cell, which connects to the RAM component, which means we are using RAM. Okay, the RAM component is active. So as soon as you know the RAM component is active, you should have an automatic answer next. Two more questions should be automatic. The next question is where in RAM? And then one more question is, are we reading or writing? So those 2 questions should be pretty much automatic. So, but I'm going to do this kind of systematically. So now we say, okay, I'm going to use this approach here. This is RAM cell. What about the next one? The next one is bit 2. So we want to look up where bit 2 is going. Bit 2 is going to RAM load. Okay, good. So this is going to, RAM load. So when RAM load is a 1, what are we doing to RAM? Are we reading from RAM or are we writing to RAM? If it takes you more than 5 seconds to answer this question, it's time to restudy the RAM component. Okay? Because you don't want to waste that time looking things up, digging through the library reference. Even though it's in the library reference, you don't want to waste that time in exam 2 because, if you can get familiarized with the components now, you save a lot of time during the exam. So you can focus on things that are specific to the exam. So RAM load is a 1 means we are reading from RAM. Good. Another question is answered. So now we have another question is, where are we reading it to? Okay, what is being updated by the RAM content? And also, which location of RAM are we accessing? So we'll answer those questions eventually. So we look for all the other ones because all of the ones are significant. They're the useful components. So let's look at this one. And the first question is, what bit is that? Okay. Well, let's see. So we got 4, 4, 4, 4. This is bit 16, 17, 18. This is bit 19. Okay. So we're looking at bit 19 of the output of the ROM. So we switch back here. So bit 19 is going to this kind of big, huge bundle here. This bundle is bit 3 to 23. So bit 19 is going to be, it's going to be bit 16 from this bundle's perspective. So we're looking at bit 16 here. It is address mux, okay, ADDR mux. And ADDR mux is a 1, okay? So what does that mean? Well, that helps to answer one of the earlier questions. When ADDR mux is a 1, it means the program counter is connected to the address bus. Okay, so we go back here. And then we say ADDR mux is a 1. And in parentheses, we just say the program counter is connects program counter dot q, which is the output of the program counter, connects to the A port of RAM, which means the program counter is now dictating what location we are reading. Is that okay? All right. What else do we need to do? Okay, we look at the opcode again. So there's another one here. So we look up this one. And this is like 4 bits down from the other one. That one is 16, sorry. So that one's 16, this one is going to be bit 20. Bit 20 is this guy. So bit 20 is going to PCEN, which means we are ready to update the program counter. Okay, so we write this down, and this is PCEN, okay, about to update the program counter. And that should be basically, that should raise a few questions, well, at least one more question right away. It's like, how are we updating the program counter? Okay, so we'll check out the last bit. Well, this is the last one. Okay, no, we have one more bit. We have this one more bit here. So let's check out what that one is going to do. That would be bit 24 of the ROM's output. So bit 24 of the ROM's output is right here. And that one doesn't go to the rest. It simply goes back to the multiplexer that feeds to the microcode pointer. So when that is 1, that means we're taking input 1 of the multiplexer to update the microcode pointer. Input 1 of this multiplexer connects to the output of the adder. So that means we'll just kind of move on to the next microcode slice after this one. Okay, but it's good to update it too. Update our little list here. Question? Yep. Say that one more time. Yep. Because we got groups of 4. We got 1, 2, 3, 4, 5, 6. 6 times 4 is 24. Huh? Correct. This is bit 23. This is bit 24. Because we count from 0. Yep. Yep.
The one which is 19, you said it's 60? And
yes, because it is offset. Because you can see how bit 3 to bit 23 of the ROM output goes to what we call Ucode data, and then it is further split into smaller units. So that's why bit 3 of the ROM's output becomes bit 0 of the splitter. So everything is off by 3 when you count it.
okay, so counting starts from 3, not from 0. That's why it's 60.
But there's a reason why. It's because this entire bundle of wire is connected to this tunnel, and that is split. So every time you split, it has its own bit 0. So this bit 0 corresponds to bit 3 of the output of the ROM. Okay? Okay, so where was I? Yep, I was going back to here to update this. So the Ucode PTR is just going to increment. Okay, so now we have one really important question that we haven't answered. How are we updating the program counter? Because on the next rising edge, the program counter will be updated. So now the big question is, how is it going to be updated? Well, let's try to figure that out. Okay. So when you look into the design, you look up the program counter, and you say, okay, so what is going to be connecting to the input of the program counter, because that's going to be the new content of the program counter? Well, that comes from a multiplexer. So now you have to say, how are we configuring this multiplexer so that we can at least know what is going to be used to update the program counter? Well, that depends on PC mux. PC mux is a tunnel, so you go look up the tunnel and go like, okay, where is it connected to? PC mux connects to up here. Whoops. Yeah, the PCI or JCI instruction is one of the more complex instructions. So PCMux is right here. In other words, oh, PCMux is not coming from the ROM itself. It is actually the output of one of the components. It is the output of this multiplexer. So what do you do? Well, the next question is now, what is PCMux then? Because PCMux is the selection of this particular multiplexer. So now that determines what is going to be the actual PCMux. Okay? So you look at PCMux and PCMux turns out to be one of the tunnels coming out of the ROM. So you just have to look up the wires here, and here is PCMux. So PCMux is bits 17 to 19, but it's splitting off of microcode data. So if you want to correspond it back to the output of the ROM, you have to add 3 to it. So that means PCMux corresponds to bit 20 to bit 22. Okay, so now we have to look up bit 20 to bit 22 and see what they are. Okay, so now we just have to decode this, right? Bit 20 to 22. So bit 20 is right here, bit 21, bit 22. So these 3 bits corresponds to PCMux. They're all zeros. Okay? Okay, fine. So now that we know these are all zeros, well, we might want to document it. So we just go like here, and then we say plus, 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 just so that this is a very crude way of using a text editor to kind of map out the bits. Okay, so this is our PCMux. Okay, so going back to the processor, like that. When PCMux is a 0, well, we kind of know what a multiplexer does, right? So when PCMux is 0, 0, 0, that means input 0 of this multiplexer becomes PCMux. So now we track that wire, okay, back to here. So it's either coming out of the, it's going into the ALU called flags in, but it's also the output of the flags register. A flags register or any register is always outputting its content. Okay, so that means PCMux is the same thing as bit 0 of the flags register. Okay, so let's write that down. Okay, so but we cannot write it down as a part of the ROM output because that actually is not a constant. So we say PCMux is now, we know it is the same thing as bit 0 of the flags register. So now the next question is, what is bit 0 of the flags register? Right? So we go back to the design and we say, okay, here's the flags register. How is it updated? Well, the input of the flags register comes from flags out of the ALU. So now we have to dig into the ALU to find out what is bit 0 of flags out. And if you look it up here, flags out is here. So this bit 0 turns out to be what we call C out. Okay. Now, if you remember, C out is really just the carry flag or the borrow flag, depending on whether it was a addition or subtraction. Then you can stop there. But if you do not remember, you track it back. You say, what is C out? So you track down what is C out. So C out is here. So C out depends on what operation we are specifying because it depends on the selector. If we are adding, it is the carry of the adder. If we are subtracting, it is the borrow of the subtractor. Okay, which we collectively just call that the carry flag. Is that okay? Okay. So going back here, so now we can now say, oh, by the way, that really is just the carry flag. Okay, cool. But now we have an issue because at runtime, you cannot predetermine what is the value of the carry flag. Okay, looking at a slice of microcode does not tell you what the carry flag is going to be. It can be 0, can be 1. It all depends on what was the previous operation that can change the carry flag. Okay, if you have a compare instruction and the first operand or the minuend is less than the subtrahend unsigned, then the carry flag is going to be set. If you are comparing 2 numbers, 2 registers that have the same value, the carry flag is going to be cleared, right? So you cannot just look at this and know, the exact behavior. So now what you need to do is to say, well, we don't know what the carry flag is going to be 1 or 0. So now you have to say, if the carry flag is a 1, then blah, blah, blah. Else, if the carry flag is a 0, then blah, blah, blah. Because you have two possible scenarios, and you cannot tell which one it is, just by looking at the microcode. So now you have to kind of think of, okay, what if the carry flag is a 1? So if the carry flag is a 1, PCMux is going to be a 1. So what is going to happen in that case? We switch back to here, and then we go to the main processor. We go back to the program counter portion, and we say, what if PCMux is a 1? Well, if PCMux is a 1, then this multiplexer is going to take input 1 to feed to the program counter, which is here. Dang it. We just run into another multiplexer. Well, it's okay. We can figure out the math of the other multiplexer too. Well, as it turns out, the other multiplexer relies on register output 0EN, negated, and PCMux to do the job. Okay? I'm pretty sure register output 0EN enable is off. Why? Because we have looked at everything that are ones already, and we didn't find that, right? So we know register output 0 enable is 0, which means the negated version of that is a 1. Okay? And in this particular scenario, we also assume that PCMux is a 1 because we are assuming that the carry flag is a 1. So we got 1, 1 into an AND gate. The output of the AND gate is going to be a 1, which means this multiplexer is going to choose input 1 to become its output. Okay, so we can now move upstream just one step. Ding, like that, right? Now, where is that connected to? Well, this answers one of the earlier questions. We are reading from RAM, but what is the output of RAM connected to? It's connected to the program counter itself. Okay? So now we know the RAM data, which is an output, connects to PC.D, which is the input of the program counter through the two multiplexers. Okay? But we analyzed the multiplexers to know that there's a path from the data port of RAM to the data port of the program counter. Is that okay? Oh, so that means the program counter, okay? So this means the program counter is doing that because the address bus of the RAM is also connected to the program counter. So it specifies the address in RAM, but we are not interested in the address. We're interested in what is at that location because we are reading from that RAM component, and whatever that is through the data port of RAM is connected to the data port of the program counter, so the program counter is now updated to what it is pointing to. Haven't we seen this before? Yep. Okay, so what if the carry flag is a 0? Then what do we do? So if the carry flag is a 0, then we also know the PCMux is also a 0 because those two are now connected by the multiplexer. Well, if those two are connected, what does it mean? Well, it's time to go back to the design. Now, I'm hoping that when you're doing this, you're not doing it with an XGA monitor, which we are looking at right now. So if you're doing this on I would print the processor architecture on a piece of paper and then do the other one on a separate sheet or using a spreadsheet or something like that. But it is particularly cumbersome when my screen is only this big. So I have to zoom in, scroll around, and then flip between the applications all day long. Okay? So when you're doing this, hopefully it's not nearly as painful. Okay, so what if PCMux is a 0? Well, if PCMux is a 0, then input 0 of this multiplexer connects to the input of the program counter. Well, that's just connecting to the adder. But wait, the adder is not guaranteed to be adding because this wire is the result of some calculation. Okay, this is 0, 0 already, so one input to the adder is guaranteed 0. But the carry in to the adder is not always 0. It's not always 1 either. So we have to calculate this OR now, okay? Well, this OR takes one input from ADDR mux, address mux. And guess what? ADDR mux is known to be 1, okay? So now we know the program counter is going to be incremented when the carry flag is a 0. So we go back here and we say the program counter is just going to be the program counter plus 1. Haven't we seen that before? These two, this is the second component of the ternary expression. This is the third component of the ternary expression. And they are dependent on whether the carry flag is a 1 or 0. So now we have a full explanation of how JCI operates. That is how I would study. But tag, this is extreme. I don't have time to do all this because there's JCI, JSI, JZI, JLI, and JOI. Well, what do you do then? You look at the differences between those, right? Guess what part is the only part that is different? They're all the same except for the PC mux part. In other words, if you look at the microcode of those 5 opcodes, now the opcodes can be way different, okay? It doesn't really matter because the opcode only maps to a location in the ROM. It is the content in ROM that is actually important, okay? So if you look into the ROM component and do the same kind of breakout, you will see that they only differ in PC mux mux. PC mux mux is going to be 001 for the Z flag. It's going to be 010 for, I think, the sign, 011 for the overflow, and then it's going to be 100 for the L flag. That's the only difference. In other words, that's really, it really is just controlling which bit of the flags register am I paying attention to. But the rest of the mechanism is really the same. Okay, so understanding that these 5 instructions are only differing in a very minor way of selecting, okay, which one is the bit that I'm connecting to PC mux, means that understanding one, basically you now understand the other 4. Okay, is that okay? And as I said, the conditional branch instruction is possibly the trickiest, one of the trickiest instructions of the entire instruction set. So the rest are actually fairly easy by comparison. So this is how I would study, quote unquote, the instruction set, is to first know what it is supposed to do from the outside view, and then you look into the actual implementation and find out how the microcode is orchestrating the components inside the processor to get a job done. Are there any questions? No questions? Okay. But this is the reason why I give you the open-sourced processor architecture in LogicSim, because you can do all of this analysis and understand how instructions actually execute and what it actually does. Is that okay? So with every semester, I'm guessing about 40% of people would actually dive into the design and actually figure out how everything works. And then the other 60% usually just kind of go like, well, if I don't need to know this, I'm not going to try to understand it. And then the exam tool will reflect that. So, but I am telling you that this is how I expect you guys to study, okay? Now, what if you don't understand something here? Well, then you have to find out what you're not understanding, okay? If it is the operation of a component, you look up the definition of that component. If you absolutely cannot figure it out, you can always ask me. But just keep in mind that my job is not to mind meld with you and share what I know, okay? My job is to ask questions so that to guide you to find that answer by yourself. Okay, so that's what I would do. Are we good so far? Yep.
Like an example of the types of questions you asked about this on the test?
Well, there are sample tests of exam 2 already online. So So that's kind of, that will give you some idea of, what I have asked in the past. But what I will ask this semester, I have not determined yet. Yep. But it will be based on the assumption that you understand the underlying implementation of the instructions. Okay. All right. So we are almost done with that page that I wrote on here. All right. So instructions. Single step, simple instructions. That's another way to get familiarized with the operation of the processor. So in addition to statically, just on a piece of paper analyzing the JCI instruction, once you think you gain I have a pretty good idea of how it works. Now it's time to design some experiments to actually see it work. Okay. So what kind of experiment are we talking about? Things that are simple, you can single clock through the whole thing, and it demonstrates, how these instructions operate. So I can give you an example. So going back to the assembler, and go to source. Okay. All right, so I'm going to get rid of this program here that I really don't need at this point. Well, it's okay. I can clear out more than what I need. Okay, so get back here. So what I would do is load the LDI-A with 5. Okay, so the register A has a known value, and then LDI-B with, I don't know, let's say 5 again. CMP AB, comparing A to B. JCI, which is the very same instruction that we just talked about, to label L1. Have a halt instruction here. At label L1, have another halt instruction. Okay, so based on our understanding of the JCI instruction, what is this going to do? Well, it will end up subtracting 5 from 5. And 5 is not less than 5 unsigned. Okay, so that means the carry flag is going to be cleared. If the carry flag is cleared, the program counter will just be added. It will just increment and skip, and it will not do the branch, and instead will do the next instruction. So in that case, it will reach the halt instruction on line 5. What if I change the program so the register A is not initialized to 5, except and it's initialized to 4? So now the compare instruction is going to subtract 5 from 4. Okay, unsigned. 4 is less than 5 unsigned, which means the borrow flag or the carry flag should be set. If the carry flag is set, then the program counter will be updated using L1, because the byte L1 is right next to the 4 opcode. So L1 is going to be put into the program counter. So we will continue execution where L1 is. L1 is a symbolic name of the instruction or byte right after that, which is the halt instruction. So if I program it like this, then the program should stop at the second halt instruction on line 7. So that's basically, so I formulate a theory first. Okay, I formulate a prediction of what the program is going to do, and then I go do it. Okay, I go to the RAM file tab, download it, load it into the RAM, run the program, and see which halt instruction is stuck at. So that's another aspect of studying the instructions, is to design experiments. Okay, based on your understanding of the instruction, design simple experiments to verify that your understanding is correct. Is that okay? And doing this, seems to be kind of like tedious, because it's a lot of work kind of to program this, download it, load it into RAM, run the code, and then stop it, and then look at where the program counter is. Well, the more you do this, the quicker you can do it the next time. So it is actually also helping you to get familiarized with the tools and understanding the entire tool chain, so the next time you actually have to do some programming, you won't be wasting that much time on, Which tab again do we download the RAM file? Or how do I get that content into the RAM component? Because you have been doing it so many times, it's just going like, okay, blink, 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 right click, blink, 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 done. So are we okay so far? Okay, so this is the reason why I'm not really providing a lot of studying material as far as the processor architecture is concerned, because the library reference combined with this is the actual studying material. I just have to tell you how I expect you to do the studying. But the material is all here. It's open sourced. Is that okay? Now, the next section of the web page that I just wrote extends a little bit further. Okay, so we talked about that already. Section 4 talks about the idea of open source. Everything is open sourced. What do I mean by open source? The architecture is completely laid out here. There's no secret whatsoever to the processor architecture itself. The ROM is also open sourced here. Now, even the assembler is open sourced. What do I mean by that? If you go to the assembler, and if you ever wonder how we get the bytes in the RAM file, it's easy. Click on it. Figure out how it gets the job done. You look at this formula, and it says, oh, it refers to 2 cells in output, the tab output. It refers to B2 of output and C2 in output. So what do? Well, you go to the output tab, and you track down those two, this one and this one. Oh, these two are in return referring to something else. It's referring to assemble X1, and the next one is Y1. Then what do? You go to the assemble tab. Okay, and then you go to the X and the Y, right? You go to, this is Y and this is X, the other one is X. You go like, okay, now it refers to a whole bunch of stuff, decimal to hexadecimal, decimal to hexadecimal, is text, and so on. It gets increasingly difficult and complex. I do not expect you guys to understand the spreadsheet itself. Okay, you just have to know how to use the assembler. You don't have to understand how it works. Okay, but for all of those people who are extremely curious and they have all the time on their hands, they can actually go look into the entire mechanism and understand how I wrote an assembler out of a spreadsheet. So even from the perspective of the assembler, it is also open sourced. What about LogicSim itself? LogicSim itself is also open sourced. You can go to the source code portion, SRC, go to LogicSim, and now you have access to all the Java source code of LogicSim itself. Do I expect you guys to look into here and go like, I want to find out exactly how a single clock works? Okay, how does it do all the simulation? No, you don't have to do that. But for those of you who are curious, it's here as well. In other words, the infrastructure of this entire class is open. But that's more of a philosophy kind of thing. But I also think that it's really beneficial because for those who are curious, you can learn a lot more than what the curriculum is listing. Okay, by digging into more things. I mean, these resources are available after the class. I mean, you can just download everything, put it onto your thumb drive. So even when you're not in this class anymore, you can always go back and take a look at things that you have access to, that you had access to. So there's that. All right. So I think I'm done with talking about how to study. So we got about 10 minutes or so, so I don't think I will give you guys any new lab today. So today we will just kind of wrap up the lab that we started on Monday. If you're done on Monday, there's no new activities today. But what I will do right now, because we still have 10 more minutes at least, is to talk about how do you convert C code into assembly code. Okay, so we move on to this slide here. So the first thing we want to deal with are just control structures. In other words, we just want to look into if then else, while loops, and that sort of thing. Calling and returning is a little bit more complicated. We'll deal with that later. So in this particular module, all we are going to do is to look into control structures. And I will give you templates like this. Okay, so this is a template of a chunk of code in C. It's the most generalized version of a conditional statement. We got three pieces. Okay, one piece is the condition, which is usually an expression that evaluates to either true or false, or in C, it is either 0 or non-zero. Okay, 0 is false, non-zero is true. We got a block of code here. I call it block 1, which is the block of code to execute when the condition is true. And then we got block 2, which is the block of code to execute when the condition is false. So that's really kind of the general idea of a conditional statement, regardless of the programming language. Okay? So now the question is, how do we translate that into assembly code? Well, let's not translate it into assembly code first. Let's translate that into C code that your other professors do not want to see. Okay? So you look at these two chunks of code. Are they equivalent in terms of what they do? Well, let's check it out. It looks like the second one doesn't match the first one because we are negating the condition here. Okay? In the first one we have C, but in the second one we have the negation of C. But wait, look at what we are doing when C is false. When C is false, I go to the label L1. Whereas L1 is right before block 2, which is the chunk of code that I want to execute if and only if the condition is false. Oh, okay, I guess it works when the condition is false. What if the condition is true? Well, if the condition is true, not true is false, so we are not going to go to label L1. So we'll just go ahead and go do whatever block 1 is. But at the end of block 1, when block 1 is all done, I have a go to here. I have another jump to L2. Where's L2? L2 is right after block 2. So this way, the then branch does not kind of continue execution to the else branch, because without this go to L2, I would just continue onto block 2, which is not what a conditional statement does. Is that okay? So the behavior of the second piece of code is identical to the first piece of code. It's just that it looks uglier. Okay? So if it looks ugly and other professors will frown on this chunk of code, why do we do it like this? What is the big change from the first chunk of code compared to the second chunk of code? Do you notice the disappearance of the curly braces? It's called flattening. Okay, I flattened the first chunk of code one level to get to the second chunk of code. It doesn't mean that block 1 cannot have its own while, if, and so on and so forth, and block 2 can be the same. But I just got rid of one level of structure. Okay, because in assembly language programming, there's no such concept as open and closed braces. There's no inherent structure to your program. So we have to flatten the program in order to do the translation. Okay, so let's move on. Okay, the second one is the easier case when there's no else portion. So that it's just a special case that's easier to deal with. So next one we deal with a while loop. Okay, so with a while loop, we only have two things, right? We have a condition that specifies when should we stay in the loop. And then we have a block of code that represents the body of the loop that we perform repetitively until such time that the condition is false, then we get out of the loop. Okay? So I'm going to do exactly the same thing. I will flatten this structured code into unstructured code that does exactly the same thing. So I have an L1 before everything because I need to branch all the way back to the beginning. And then I have a conditional statement. The condition of the conditional statement has the condition negated because in a while loop, C is representing the stay in loop condition. Okay, as long as this is true, stay in the loop. But when I use the conditional statement, I'm looking for the opposite. I'm looking for the reason to exit a loop. So that's why C is negated. and then the go-to of this conditional statement goes to a label that is outside of the loop. Well, what if C is true? Well, if C is true, not C is false, I'm not going to L2, so I would perform block 1. But when I'm done performing block 1, I have to go all the way back to L1 because that's what a loop does. At the end of the body of a while loop, you go back and re-evaluate the condition to see if it is time to get out of the loop. Okay? So once again, the original block of code, or the original code using while is structured, and then the alternative that I have translated here is unstructured. Okay? Once again, we have flattened the original code so that that level of structure is gone. Now, what if block 1 has its own structure? Well, recursively apply this method to block 1. Okay, so moving on. Post-checking loops are relatively rare. Okay, I would estimate in my own programming, maybe 2 or 1% of my loops are post-checking loops. The rest are all pre-checking loops. But since it is a structure in in C and C++, let's talk about it. So we have do, and then some block of code, while, and then the condition here. So the translation is a little bit different from the first one, but it's the same idea. L1 marks the beginning of the loop so that we have a place to go back to. Block 1, but this time block 1 is performed first before we even evaluate the condition once. And then when it's done, then we simply ask, is the condition C true? Because if it is, we go back to L1. If not, we continue with whatever is after the do while loop. Okay, so it's actually a pretty easy translation in this case because we don't have to negate the condition. All right. So, wait, but there's a problem here. The idea is if C is simple, like comparing this to that, checking for equality and stuff like that, it's easy to deal with, okay, because we have a compare instruction, and then we have the conditional branch instructions to help us decide, well, should I branch when these two values are the same? Okay, so we kind of know how to do that. But what if C has a conjunction in it, and the two sides of the conjunction have nested disjunction, and then inside each disjunction has negation of something, so it's a complex Boolean expression. What if C is complex? That's the next question. Well, we got ways to deal with that too. Well, if we are dealing with a negation, you can always get rid of a negation just by saying, if the original thing is saying if C is false, go to L1, we can always turn it around and say, if C is true, go to a quote-unquote bypass label, okay? But if we're not going to the bypass label, that means C is false, and in that case, we go to L1. So it accomplishes exactly the same thing, except the negation is gone. So this time, we are not flattening at a statement level. We are now flattening at an expression level. Okay? Because C can be a huge, big, long Boolean expression. What do? Well, we just recursively make it simpler and simpler and simpler. Okay? Okay, so this is for negation. In addition to negation, we also have and or. So deal with the or first. So if the original expression is an or expression or disjunction, and it looks like C or D, and remember, C can be huge and complex on its own, D can be huge and complex on its own, okay? All I'm trying to do is to get rid of one operator at a time, okay? So if C or D is true, we go to label L1. Oh, this one is pretty easy to do. If C is true, that's enough reason to go to L1. Well, if C is not true, then we check D. If D is true, then we also go to L1. If C and D are both false, then we're not going to go to L1. We'll just continue to do whatever is next, which matches the behavior of where we're translating from. Is that okay? We only got one left, which is and, right? So here's and. And is a little bit trickier because if the original expression is if C and D go to L1, which means if C is true and D is true, then we go to L1, then you kind of have to check the opposite or the negation of C first. Because if C is false, We'll just kind of go around. Okay, we go to the bypass label. Okay, because in a conjunction, if one condition is false, the whole thing is going to be false. And C and C++ actually has short-circuited evaluation specified as a standard. Okay, so this is the actual specified behavior when it comes to a conjunction. And a disjunction too is also short-circuited. If C is true, then we are not going to go to L2. Instead, we'll fall through to the second conditional statement. The second conditional statement says, well, C is true, but what about D? Well, if D is also true, then we go to L1. What if D is false, even though C is true? Well, we still fall through to L2, which is the bypass label. Is that okay? So now we have addressed negation, conjunction, and disjunction, the only three logical operators defined in C, which we already know is redundant because we know everything can be done with NAND. Okay, some of you remember NAND. So now we have a way to flatten statements, and we have other ways to flatten expressions. So when you flatten expressions all the way, okay, what do they eventually boil down to? What is the end of the flattening process when you're talking about a condition of a conditional statement or the condition of a loop? If you flatten all the way, down at the very bottom level, what do you get? Comparisons. Okay, they end with comparisons. So you can have implicit comparisons of is it 0 or non-zero, but it's still a comparison, okay, because you're comparing with 0 and see if it is the same, okay, so that's a comparison. Or it can boil down to less than, greater than, less than or equal to, greater than or equal to. But those we can handle. We know how to compare. We have the JCI, JCI, JSI, JOI, JLI instruction, so we can handle that using assembly instructions. So that means if you apply these processes recursively, then we eventually get down to a level where we can specify assembly code to deal with the rest. Okay. So the next part talks about, we are running out of time, so I'm going to stop here. So section 4.4 is where we stop today. There's no new lab activity today, but I do want you guys to quote-unquote study the instructions, the opcodes, the way that I just described earlier in class. And today is a Wednesday, perfect, because you have a longer, like 4 days before we meet again. So that would be an excellent amount of time to work on what I suggested today. And of course, every single professor on Wednesday would say the same thing. So you still end up with a big, huge pile of things to clear before next Monday.